Yeah, okay. So yes, when you're looking at number 1 on the lab, this part that says watch this video is a link that you need to click, and then you need to watch the video. There are answers to the lab in the video, specifically, and I'm going to briefly skip ahead just to show you what it looks like. There are several parts in the lab where it says, pause this video and record this in the data table under massive aluminum foil. It like says that in the video. So that's when you need to like pause and record the data. It's hard to see, there's a decimal point in there. This is 3.94, not 394. I'm just throwing that out there. But like if you look at a lab and go look at number 2 is a data table. The part of the video where I paused it said massive aluminum foil. So we're going to put that 3.94 from the scale in the video in this box in the data table that says massive aluminum foil. If you're paying attention, I just gave you the first answer. So you should probably put that in your lab before you forget. The rest of this data table, some of the numbers, the ones that are labeled in blue, this B and D, those numbers are straight out of the video. It even says that right here. The blue parts of the chart should be taken directly out of the video. The red parts of the chart will require you, oh crap, I just accidentally went backwards. It's okay. They will require you to use that brain of yours. There's hints under the data table that tell you to subtract some stuff. And that's going to be how you get the rest of those answers. So the 3.94 from the video is the first number that goes in here. This B and D that are in blue are also directly in the video. There will be a part where Mr. Dado pauses the video and then tells you in a caption to pause the video and write the number down. So you should like do that, okay? And then if you look at the bottom here, there are hints about finding these red ones, C and E, massive only steel wool, massive burn steel wool. It tells you exactly what to do to find those numbers. I am going to briefly talk about the chemistry that is happening in this lab using this extra video A here. So please there's a thing to click on in number 1. Okay, I get it. I will watch at least the first video with Mr. Dado. So make sure you actually click that. These extra videos are just faster, like shorter videos with the same phenomenon that Mr. Dado's doing. And I'm going to talk my way through that one that's labeled extra video A to just kind of get us all a basic idea of the chemistry that is happening. So you see that they've got like a scale. There's like a pie tin on it, and there's a big thing of steel wool sitting in the pie tin. The steel wool, if you don't know what steel wool is, it's steel, like metal, and they like pull it into these really, really, really thin wires, and then they like tangle it up. So it feels kind of like raw wool, like when you like shave a sheep, right? Except it's like sharp. But it's like just this big ball of tangled wires, basically. And they're really, really thin. And we can see at the beginning of the video that the steel wool starts at 27.35 grams. And then in the video, they set it on fire. And they get it burning real good. And you can kind of see the fire spread. It's like really pretty cool looking, mesmerizing. If you look at the scale, the mass is changing. Right now, the mass has gone down to 27.25. And you're kind of like, okay, yeah, I mean, I kind of expect stuff to get lighter when it burns because you're like losing a lot of mass to like smoke and stuff. But then suddenly that mass is like now skyrocketing. It was at 27.35 before they set it on fire. Now it's past 28. It's just going, going, going. That mass is going up. Why is something getting heavier while it's burning? What? Why does that happen? And the answer to that question, why does that happen, is what this lab is about. So This video is just sort of like a shorter thing of the same basic thing that Mr. Dado is doing, but I just wanted to kind of like emphasize what's happening here. As the fire is almost out, the mass is now up over 29, and then it ends up stabilizing at 29.10. So that means that if you're, kind of thinking about how math works, the ball of iron gained 1.75 grams. It got 1.75 grams heavier from burning it. And I see David in the chat already knows what's going on. I'm going to back it up a little bit conceptually, but someone's on top of things. So casual reminder, go back and do the data table on number 2 using Mr. Dado's video, but I want to look at number 3 with you briefly. It asks, why did the mass of the burned steel wool increase? Basically, why did it get heavier? And you have to think about some ideas to answer this question, but the bottom line here is that we started with iron, that's the steel wool, it's basically iron, and then we lit it on fire. How does fire work? What do you need to make a fire happen? You need 2 things, right? You need a fuel, and then what's the other thing you need for fire to work? A fuel like wood or food is normally, or like gas on a gas stove, normally what we think of. Or in this case, it was the iron. And then, yeah, oxygen. You need oxygen for fire. You need fuel and you need oxygen. So the fuel in this case was the iron. And then we had the oxygen here. When it was burning, it actually ended up creating iron oxide. This is specifically iron 3 oxide, which is a type of rust, basically. That's the most basic version of it. It's kind of like a type of rust. It's heavier than the steel that we started with, because the steel that we started with was a bunch of iron atoms. And at the end, they have actually taken oxygen atoms and glommed onto them and stuck them together. And now we've got this compound instead that is heavier than the element we started with. Where did those oxygen atoms come from? Steel is usually a small percentage of carbon as well as sometimes chromium, depending on the grade of steel. But the carbon in this is not appreciably reacting because it's dissolved into the iron. They take iron metal and then they melt it down till it's red hot molten, you've probably seen on TV or something. And then they throw chunks of carbon in there, like graphite, and then they stir it and they get it a certain mass percentage carbon, but it's usually a small percent carbon, less than 10%. And then the rest of it's iron. The carbon is not appreciably reacting in this particular circumstance. But yeah, the oxygen comes from the air. So the iron was burning, taking oxygen atoms out of the air, and then combining to make a compound. And since that compound is iron oxide, it's each piece of the compound is not just the iron atoms that were already in the steel wool, but now also adding on oxygen atoms to it. The whole thing's getting heavier. I did just give you the answer to this problem if you were paying attention. I don't need you to write an essay for this. Neither does Mr. Dado. Neither one of us is an English teacher. Neither one of us wants to read an essay, okay? Give us a sentence. That's all we need. Some of you might be able to efficiently answer this in 6 words or less, okay? I just need a short, sweet, to the point sentence explaining this. That's all I want, okay? And then looking forward to number 4. Number 4 has 4 sub-questions. I'm going to point out that Schoology has a button to make a numbered list. Please number your answers the way these questions are numbered. And again, I don't need an essay here, okay? Some of these questions on number 4, you can give me like one-word answers too. Like question 1, what evidence did you see that the chemical reaction occurred? I can think of multiple correct one-word answers. I would love for you to give me just a one-word answer here. And Mr. Dato's class, similarly, he would love just a one-word answer. It's so much easier for us to grade. And it's March 2021. Like, we don't have the spoons to be grading essay length questions. Okay, like please just give us the one-word answer where you can. I do want to point out, exactly, that is one word. It's a beautiful word. I do want to point out that number 2 and 3 do involve knowing our new vocabulary, limiting and excess reactants. Remember, the limiting is the one you run out of. The excess is the one that there's extra of. They might be easier to answer if you actually think about number 4 first. Number 4 asks, what would have happened to Mr. Dato if both reactants were completely consumed? Completely consumed means like totally used up, where there's none left over in the room at all. So one of your reactants is iron, the other one's oxygen, and it asks if both of those were completely consumed and there was none of either of them left in the room at all, what would have happened to Mr. Dato? This is not a rhetorical question. I'm asking you, what would have happened to him if all the iron and all the oxygen in the room had been completely used up in that reaction? And there was none left in the entire room. What would have happened to Mr. Dato? None of you are brave enough to answer me? Yeah, thank you. Thank you. He would have died. Spoiler alert, that is not why he's not here. He's doing like family stuff today. He is alive. We kind of already knew he was alive because like if he had died, he wouldn't have been able to upload the video, right? But yeah, he'd be like so dead, which he is not dead. So knowing that he did not die, that should tell you which one of these had leftover and which one of these we ran out of. You know what I'm saying? He didn't die. So one of these, there was leftover in the room, and the other one we ran out of. So that's just something to think about when you're answering questions 2, 3, and 4 in here. I also want to give you a couple notes on number 5. If you want to look ahead to number 5, this one's an actual stoichiometry problem here at the end of the lab. It says, calculate the theoretical yield of iron oxide using the initial mass of the steel wool. Look in your data table from question 2. Initial mass of the steel wool, that number for the initial mass of the steel wool in the data table, that's going to be the given you put in this box. What goes in this first box as your given in part A is a number from the data table, okay? It does say to round your final answer here at the end. I want to give you some hints about the conversion fractions. Your starting number from the data table is going to be a number of grams of iron. You can notice they did what goes up must come down to like cancel the grams out. And then they converted to moles. Please remember, a gram to mole conversion, that's where your number of moles is 1. And similarly, in this third fraction, they have moles of iron oxide and they convert it to grams of iron oxide. A gram to mole conversion, that's where your number of moles is 1. Where do the grams come from? Thank you, Lucy, periodic table. So this bottom box, that's grams of iron. In this fraction, that's going to be a number from the periodic table. Similarly, this top box on this other fraction, that's grams of iron oxide. That's going to be a number from the periodic table. This middle fraction, on the bottom, they have a given element. And on the top, they have gone into the unknown. Okay, Mr. Dato's kids, I don't know if you've been watching his videos or my videos, but if I just surprised you by singing again, none of my kids are surprised. That's all I'll say. When you go from the given into the unknown, that's where you have to chemicals.
The good cop, bad cop routine.
Where you change chemicals is going to be where you take your coefficient from the reaction, and that's the number that goes in your fraction. The number and the fraction has to come from the reaction. The number and the fraction has to come from the reaction. Okay, so those are some hints for you. This bottom part, part B, asks you for percent yield. Percent yield has a formula that is probably worth knowing. I'm actually going to paste it into the chat here. If you want to copy and paste it, you can use this little notepad tool. Copy and paste it out of the chat into the notepad so that you have it later. This is for, you need this for number 5B. You need this formula. Actual yield on top, theoretical yields on bottom times 100. They tell you in part A that you're finding the theoretical yield. Your answer to part A is the theoretical yield. And the formula says theoretical yield goes on bottom. So that's your answer to part A is going to go on the bottom in part B. And then if you read the question, it'll tell you where to find your actual yield. Yeah, that's all the hints I have for the lab.